Now that's better.
Is that better?
Live stream?
Much better, whatever you did. Hi.
Ja, schön. Wie macht man hier Vollbild? F11 oder was?
Sorry, do you want me to? Yeah, okay. I can stop sharing that maybe. Is that better?
Live stream?
Much better, whatever you did. Hi. So when I do this, I should do full screen. Yes, it's actually readable. It's very well readable. From a presentation point of view, it's better than sharing a screen with anti-aliasing, I think. So this pre-uploading is actually helpful when you upload PDFs, I think.
Oh.
Maybe then the others can download it later. Can you well see that? I just did that for test reasons, but I could also present another one and see what happens.
Yeah, we can read. I can read that anyway. It's very clear. Yeah.
And that, just in case I wanted to show you that. This slides, quantization applied. No, it doesn't switch. I think you have the control what I can do. Maybe
Oh,
I
okay. Yeah.
change.
So yeah, I thought you were able to switch it.
No,
so
not.
I think I can change that. Is that a different one? Yeah. Yeah, it is.
I have uploaded 3 just for demoing, and
yeah,
that is what I wanted to switch to. Can you switch? Obviously, but I can.
Okay, so I can do that if you want, of course.
No, it's just in case we have to know and learn that, and that's not. I have tried that a little bit in the last hour with my own account, but I had no one to play with on the other side, so I'm not sure what is not possible.
Okay. So that's all good. Where did Rajan disappear to? He's dropped out, did he? Maybe he made a
He had
message.
told that he was not visible or something in the last chat, I think. So for explanation, I might be anytime interrupted as I'm sitting in the hospital in Munich here, and on a hospital Wi-Fi, and when they come in to do some examinations or whatever, they might try even on weekends at any time. Then I have to go mute and go blank for a time.
No problem. Okay. So if it gives the following underline, oh yeah. So I earlier I managed to add you to the stream, Christian, and then but it was too early, so I stopped, and then I forgot how to do it, so I had to look it up again. But it was really simple. It was just press a button. So
yeah, the tool seems not bad. Have you bought a TEGS license for a monthly fee or something, or because I think
no, this is like what you were saying. I just just the free version.
I can do 6 people only, I think, or 10. Was it 10?
Oh, I actually don't know the limits. Yeah, I haven't checked that out at all. So might be something worth doing.
But the optical thing, what is the presentation style, including the naming, and this is much better than many other things I have seen. It's actually quite clear from the technical. See, Rajan is playing. You can overlook him. I saw now he injected a text that you don't overlook the text. So this is actually well done by streamers. Is that a daughter of Google, or is that a daughter of Facebook, or what is it actually?
Well, where are you looking? Sort of.
Is StreamYard a daughter of Google, or a daughter of Facebook, or?
Oh, right.
YouTube,
actually.
Google, yeah.
Oh, is it? I don't know. Okay.
I had not much time to do anything in the last weeks due to the medical stuff appearing here unexpected.
Oh, yeah,
but
fair enough. I was thinking, yeah, we do like just sort of beta test this whole thing, and then maybe we could do like some kind of just like a general sort of talk on things, like general. That might be better. Yeah, so.
To see the chat, I have to exit full screen. That is fine. So this is an individual. You don't see when I exit full screen, right? So I can do that without you.
Yeah, no, we don't see any of that. So you can present as well, can you? Slides. Oh, you can share screen. So that might be easier for you in future, Christian.
Talking to me or?
Yeah, I was just saying you can share screen as well, so that might be easier.
Yeah, I can try sharing my screen. Wait a moment. What's this option here? I never tried before. Sharing screen with at least 2 monitors. Sharing works best with a good computer. Chrome. If you like to share audio of your screen, share screen.
Oh, I need to let Roger in. Sorry.
I have the choose
hello.
iSpace presentation full screen.
Hi.
Sorry, I didn't see you.
Oh, can you hear me now?
Yeah.
Yes.
I can hear you.
Oh, okay. You have to do the share screen, huh? You have to press the share screen. Okay.
Yeah.
Oh, okay. Yeah, it's good. Christopher, nice seeing you. Christian, good. Yeah, I think this is now. I think the first level is working now. Now we have to find out how to do the presentation, things like that. But then it's okay. We go one step at a time.
Absolutely, yeah. I don't even know if I have. Oh yeah, there's. Let's see if I could present like even PDF.
Is that all okay?
Can you see the mathematical screen?
Oh, let's see. No. I can't see
I'm just
anything.
sharing it now. I'm not sure if you're presenting it back because I see
do
still
I?
the.
Oh, okay.
Yeah, at least this is not automatic. I'm not sure you're like the regime manager. This is a bit difficult for you probably now because you're in charge.
Yeah. I'm wondering, what are you sharing though? What does it look like?
My desktop.
Oh, yeah.
I wondered what happened when you recursively, because I display the videos and would recursively display and share it. That can be this is what I would expect. See, and these novel systems cannot cope with that, but that system seems to be able to handle it recursively because it's infinite, of course.
Oh, so many.
Yeah, and it works with the proper delays, so it doesn't crash and handle it. This is fine. So when I go to the primary screen, you see, of course, the mathematical screen, and I can do very important calculations here in appropriate size.
Great.
So basically, then I stop sharing again. The Leave Studio button is right where it shouldn't be.
So
if I click it, not sure it kicks me out here. I need to click Freigabe beenden. Why does it tell me in German? I switched to English for my UI. Not sure. So
you had some interesting comments there, Christian, about the streaming technology. I didn't get a chance to read them all, like comprehend everything you were saying in numbers.
Yeah, it's not so important. I just compared it with what I'm used to with other streaming problems we have in work typically every day. So
okay.
Teams is good, but not that good, and wanted to see what it can do. So I'm impressed with the background features. They work well if you do what they say. So now I have an iSpace background, can even flip my iSpace background in real time, I think. Camera is mirrored, so when I point my finger to the left, this is the hexagonal iSpace, and this is the iSpace P4. Would you see the fingers on the right side or the wrong side now?
Yeah, you're right.
I'm pointing to the Pi 3, now I'm pointing to the Pi 4.
Yeah, exactly. That's clever.
When I don't mirror it, you get mad with the flipping of the fingers, so this handles properly. You need a mirrored image and a mirrored camera, and it works.
That's good. How do you mean the
should be able to change the background in real time, even to? Yeah, do you see the change?
Yes.
Yes.
Yeah.
Okay.
We don't
then
see anything.
Also.
We see only our videos.
No, he's talking about the background, Rajan.
The background.
I just switched my iSpace background to
okay.
Just to see if it's possible. Nothing serious.
Yeah. So that's cool. So is anyone working on any research at the moment, Rajan or Courage?
Yeah, there's many different areas, but main thing is using, the last one I published was the, we published theoretical to experimental with Manuel and Emery. I think I put it on the research gate.
Oh yeah, that I enjoyed that actually. I thought it was very interesting research. And
Yeah. And you helped me with all the graphics and other things. So I have,
yeah, I think it came out really well actually.
Yeah.
There's a lot in it. Like it was quite dense in terms of its subject matter, which was
maybe I
nice,
can,
you know.
should I
You know the way
project it
sometimes
now?
things can be a bit too specific or something, or specialized, and it can be a bit dry or something. But yours was took into factor a lot of considerations, and I think that's what makes research, you know, good research good. Often is when it's diverse, I suppose. The right word.
Thank you. Yeah.
Yeah, contains a lot of different concepts.
Should I project it now or something?
What?
Can I? Should I present it? I mean, should I try to put it on?
Yeah, I'd love to like, see more about it.
So share screen.
I don't know. Did I ever present the work I did on the Kummer surface? I think I did prior, but I don't know if I never uploaded it. I don't think. Sure, maybe I'll do it.
So let me see. Yeah, I think I can. Let me try this one and see whether it's coming up. Can you see now?
No, not yet. Oh, wait a second. I need to add it to the stream, do I? Sorry, you're gonna have to ask me in future because I probably forget.
No issues. So
Is that it? Yeah, that's it.
Yeah, can you see?
Yeah, we can see it now.
Here it is.
Okay. So this is published in the Research Journal of Modern Physics. So yeah, I'm going over this money. This is one of the things. I mean, other than Emmanuel, the first work, this is the one that took like almost 6 months because many things we are going back and forth on this one. So let me try. How do I move this one? Let me see. Oh, I have to go to first or second slide.
I think you just click on the thumbnails on the left-hand side, do you? Or you could probably just down arrow it as well.
Okay. Showing one screen. Oh, there's a moment. Do I have to go back to the? Oh, can you see? Is it moving now?
Yeah, it's moving now. You see it.
Oh, okay. So I know. So I think I have to go in that screen and keep doing it because when I am doing in this screen, it doesn't move. Okay. So I thought it will move in real time. Let's see. In any case, so I will just go into that screen and keep working.
What stream are you talking about, Rajan? The stream
the paper I'm presenting.
Yeah.
So I have to be on that screen, I think, because. So I'm trying to see. Okay. Trying to see how I can move it on the screen.
Probably I will switch my video off because I don't want to overload the hospital or the clinic's Wi-Fi here.
Yeah, I think I saw
it. Pretty good, but I think I stop it until I do some presentation.
Okay, fair enough.
Yeah, we are trying to figure out. So I think we will figure out pretty soon. Because I thought I had gone to that screen. So let me try pressing that and going that screen. Okay.
So Rajan, is the problem that you can't see what you're presenting and
Yeah.
the stream at the same time?
Yeah. So I think
So
I
you
have to
can't
mute.
scroll.
Yeah. Now I think, but you can see, right? So I
We
will
can
just.
see it. So
Okay.
yeah.
So now I will just be on that screen because at the top it says, what it is that it says you're presenting. There are two tabs. One of them is the view tab, stream yard, and the other one is view tab, the present paper tab. So I have to go to the paper tab. Then I cannot see you, but that's okay.
Yeah, that's fine.
Yeah.
Just whatever makes it
But you
easier.
can see now, right? So let me go over this. You can see now, right?
Yes.
Okay.
I have extremely audio problems with Rajan. The sound is only has basses, and the higher tones are missing. Maybe it's your plug of your microphone. The video is very good, but I have only basses, and I cannot understand any word.
How about now? I mean, how about others? Can you all hear me?
No.
It's a little
all
better.
other
I can hear you.
contributors have a very good sound, but only yours is. I cannot understand. Only it's too low.
Let me check.
It's a little bit. It's a bit clearer now.
Not the volume. Not the volume. The higher frequencies are missing.
Oh, okay. Let me check the audio settings. Let me check the.
That is true. You sound through an equalizer, like everything above 4K kilohertz is switched off about.
Mm-hmm.
Yeah, it's a little muffled, I guess.
Speaker.
Can it be the transcontinental line, effect of the transport physics?
No, the video is okay.
How about now?
Yes, but only the sound is. I observed the same problem on our 1 week before with the other with the other system we are using we used and for a short time, and then the sound immediately was okay. I don't know what you have. Maybe that you can plug on and off your headset or.
Okay, how about now?
Know.
Yeah, I think that is better.
Much better.
Yeah.
It's better.
Yes.
Whatever you did is much better.
Can you hear? Good. It's okay. Good.
Yes,
It
very
sounds
good.
completely normal now. It's perfect.
Normal. Okay, so I'll keep it on. See, what I did was I had the headset, but also I had direct from the I think from the computer, and the computer one working I think better. So anyway, I'll keep it. I have both on, so whichever is working is fine. As long as there is no echo, it's okay, right?
Yes.
There is one other issue though. Would you be able to close the thumbnails on the side of the PDF?
Yes, to increase the size of the presentation, we have to go full screen to properly read it. And when you close the thumbnails,
how about now?
Full screen, then it's about.
I think there's like the 3 lines in the top left-hand corner. If you click on them, there's a drop-down menu, and you can select hide thumbnails. No, the lines on the other side. Sorry, top right.
But there is a full screen modus available on the right down. If you go with the mouse right down, then there is a full screen modus available.
That you need in addition locally, but when Rajan needs to switch the left side off, or the document becomes not the full width of the screen. You need to scale up.
So let me check.
If you go to the 3 lines next
Without
to
the 3 previews on the left side, it would be better if you have a chance to switch the previews.
Oh, the 3 lines.
No, there's 3 dots. Yeah, it does. Yeah.
How about now?
Yeah, that's better.
Perfect.
Yes. Okay. See, at the top one, I have to probably hide it. Let me see. Yeah, I will try to figure out. I don't want to mess it up, so everything goes away. a little bit.
The height is not much, but this is okay. From the 16:9 readability is okay. Leave it the way.
Normally you can adjust the screen so that you remove the top displays, you know, except the. But I'm trying to see. So you see all my operation, huh? Whatever I'm pressing, you can see.
Yeah, it doesn't matter. It's fine. It's readable.
It's okay now.
That's right.
Okay. So for now, we'll continue. I don't want to. I had to find out if any other way we can. Say fit to page, but that doesn't work.
That looks good.
Yeah. Okay. Okay. So
opinion.
we'll continue with this for now. So essentially, this is the paper. I'm not going to read out everything, but essentially, I'll go to some pictures. Okay. So this is the equation. I'm not going to go over this. I was telling all the time about how I found this is a black box. The universe may be a black box. This is the equation. It's a long transform equation. Everything is transformed to time scale, rotational, and things like that. So it's like a 20-page derivation. And at some point, I will present that. But it's very quite interesting because I found that the Lagrange or Hamiltonian has a problem. Because again, the space and things like that comes in, and that creates a problem. But I removed all that. Only time is there, and it fits in with myself, Emery Taylor. We are working on the. We have published the discontinuum physics on physics essays. You may have seen. So it fits in with all that, and so it only describes time in terms of the gauge field. So the space is removed. I think the space creates problem, and also the mass. Mass is a big problem. So the mass is removed with the transforms. So only these things appear. So there is no problem of charge. We don't have to worry about the charge or mass or anything. Only the field, only the gauge field. So I'm not going to go over again. It's a very long thing. It's a presentation by itself. But essentially, EGR is a scalar space quantum gauge field. And then I can convert to time, but the time itself is a 4-vector matrix. In another paper, I describe more why it should be a 4-vector matrix, not just linear time, things like that. I have questioned that. So and then in certain cases, it becomes like linear time that we use right now, you know, with our clocks. But essentially, it has proper time, real time, global time, local time. So it has this variable, and I kind of proved it with the light and sound, how that works. So I have a brief derivation about that in an earlier paper. But again, essentially you can, so this is very important. So this time then tells us we cannot use the time that we are using. And that may be a problem. Like I say, it's 8:57 now, or 8:58 here. And then we convert to global time, UTC, things like that. But that's only a linear, very arithmetic time. But I think we have to work with the algebraic time. Anyway, another time we'll go over that. So this one describes briefly, going over this, how we can convert to gauge vibrational string parameter. So this is called matrix protocol. Essentially, you know, one of the problems is the plotting itself, graphic plotting. So if you plot just time and temperature, things like that, you get all kinds of curves. Sometimes what happens is gives a spurious result. The idea is that we have to know the underlying physics. And once we know that, we convert the x and y coordinates such that we get a linear plot. So we have to use the equations that properly describes that, and we adjust to that. We get a nice linear plot, and we can use regression, and we can find out 4 sigma level or 3 sigma level and outliers, things like that. And another earlier paper I have described that, but essentially we can write y as a function of some slope times the intercept. This slope, this y actually is not a normal y-axis or a x-axis. It's adjusted, transformed y-axis and x-axis. So Einstein, for example, transforms not the axis, but the variables. But in this case, the axis itself is transformed. Okay, so that we get a slope intercept form, and that is a very we have to know the physics, otherwise we cannot do that. So we have to go into a physics and do all kinds of transforms, adjustments to that. But there is no assumption, or there is no, we don't just fit into, or we don't assume that we fit into the things or anything like that. We don't, what I call force fit things. We take the things the way it is, except that you have to know the physics. And that's why last time when I did the presentation about observer physics, so we had to go to the minute aspects, try to weed out the problems that cause inconsistencies, the standard model, things like that, and relativity theory, quantum, and everything by using observer. And something I am going to concentrate later on in the next papers, like 3 or 4 I am working on, maybe up to 5, is how we are mixing the observer. I think that's the problem. We are looking at from one observer point of view, and they are mixing the observer with superluminous, for example, subluminar. So, for example, quantum superposition is actually seeing that subluminar observer is looking at the universe versus superluminar observers observing at the universe. Both should be the same. So we do superposition. So it's actually a mixed observer problem, I think. Again, I'm going to go into detail later on. But right now, essentially, we can express point to point. That's the idea. Each point, we find what the signal to noise ratio is. And that's what this matrix is. And that is equated. I had derived this earlier. So this gamma omega dot r is essentially signal to noise matrix, point to point profile density intensity matrix that's measurable by this equation. Okay, so there is a whole lot of things involved in this, but essentially we can convert to the normal quantum things, a Ket matrix and a Bra matrix. So the Ket matrix I can convert to this form. It's like a quaternion. You have to use, again, it's a conversion of this 4-vector matrix of the time. So you have to use 4 vectors. So it does come into 4 vectors. So the quaternions are involved, like Christopher, other people who are all presenting. And eventually, I think I can match with even iSpace and Gertz, circuit, things like that. It does seem to go into that, but it takes a few more papers to get to that. And at some point, I will put out those papers. Maybe I'll just publish a brief version of these papers myself, and then you can see, and then all of us can work together and have a combined paper eventually. That's why my hope. We can put together everything. So I want to weed out. The idea is to differentiate so that everybody understands what it is and come to a simple physics. And that's hard, because when you go into the mathematics, again, it gets into a lot of details that it's very hard to discern from a normal level of understanding of physics. But I want to do that. I want to reduce it. I believe in reductionism, reduce to a simple things that we know from high school algebra, things like that. That's all it should use. And maybe a first level calculus, not to the level that it takes us the mind out of that normal understanding. So that's what I'm trying to do. I keep coming back, so I reduce it. So this Ket and the Bra matrix does express, we remember the PDP circuit, it has a clockwise, anti-clockwise, south and north pole. the clockwise and anti-clockwise are the positrons, electrons, rotations. So the wave function of these positrons and electrons. And what happens is this, and also John pointed out, it may be like unparticle. So all of them are not really particles, but unparticles, which means they have special characteristics. They are not the usual particles in the PDP circuit. So they are created almost like quasi particles. So they exist, for, from the superluminous. That's the fundamental superluminous planum, which is like a turbulent superfluid. So the superfluid. So essentially, you can call it superfluid, but it's turbulent and it has monopoles and everything in there. So we cannot see them. So they may appear as dark matter. So that it cannot be seen. So they are superluminar superfluids essentially. But we can prove, I think eventually I want to prove that in any turbulent situation, we have a local vortex like eddy currents that we see in sea, like in Atlantic Ocean. So when you have this turbulence, locally they can create vortexes or eddy currents. I think that's a very important thing. And that creates what I call topological defects. And that creates, the topological defect is the reason for charge and mass and everything. And that's the way the real universe is created. That's the first points or progenitor, I'll call it, of the real universe, the matter universe. In any case, what I'm saying is that we can so going back, there's some more details, but going back, we can use all that to actually measure. Let me reduce a little bit so I can see the whole thing. Okay. I think you can see the picture now, right?
Yeah.
Yeah.
Well,
is it okay now?
Yeah, that's it.
Yeah.
That's
okay.
the picture.
So thank you, Christopher did the graphics for these earlier, the earlier paper. So so you have the light, the light as the the vortex downwards. So it is the gradient. What is the gradient? One is the vortex. So this light appears as gradient, but it's questionable that it could be a torsion field. Could be a torsion field that Christopher is talking about. So it can account for that, I think. So this is a gradient of the scalar field that produces light, and then you have the vortex, which is the sound. So you have vortex downwards. The vortex, it should be curl of that field. So you have the gradient of the field, almost like a Maxwell equation, but it's kind of a modified Maxwell that I give. So it's a gradient gives the light, and the curl of the scalar field will give the sound. That's my one of the key things here. So the vortexing action is taken into account, and actually it should be the gradient. I should have corrected. And anyway, that's fine. So I think I described that. So this gradient. So that's the main thing. So that gives us a way to measure. So the oscilloscope, you adjust the instrument such that we can capture the gradient of the field. We can get the wave signal that corresponds to light, and then we pull out the vortex, which is the curl of the gray thing. If we can measure that gives the sound. So we can separate the light and the sound that way from each point. So the idea is point to point. So if we see any astrophysical signal coming, could be a cosmic microwave background or gravitational waves, things like that. We actually put through this system, which is I'm showing the design, but we actually have to develop this system. So if such a system is eventually developed, we can pull out the cosmic CMBR or the gravitational wave and then feed into this one, and then we can get the light component and also sound component, not from point to point. So each point, so that's the idea of the observer. We should be looking at the point. The observer should be far enough, so we see as a point, because we go close enough, we have a lot of striations and other things. And when I did X-ray diffraction, I found that's a very important thing, that if there is striations or some kind of thing that is showing up in the picture, it's not clear, it's not a one point picture, then we have to consider the physics of that, which is highly complex. So the idea is that we go to this point level and we analyze that point, almost like a perfect point. Then we have the diamond chips embedded. So theoretically, we can do a theoretical thought experiment, and it can give a lot of information actually, about close to 50%. The other 50%, of course, we need an experiment. Like Gerd has given the circuit, and the circuit is proved right. Then I think we don't need to do so many experiments. It's like induction process. Think of a very simple calculation of the arithmetic progression. We can do actually numbers. If n equal to 100, I can add like that, or put in the computer. But instead, you use a formula, n times n minus 1 by factorial. And that's a nice formula. That's what I remembered from high school. That algebra is a fantastic algebra. So we can use algebra to actually, convert our, difficult, complex things into a much simpler way of calculating. So this is the idea of point to point, and one of them may be a microprocessor like a piezoelectric, which gives more of a sound or vibrational aspect. And then we have oscilloscope, which gives the light aspect, wave. Of course, the question in the oscilloscope is the light or the photon, is it a particle or a wave? That question, again, we have to look into that. So I consider all of them, inclusively. I don't leave we don't leave anything, because all these are very important, like double slit experiment. Especially John was talking about. I was thinking about that. I had an explanation, but I'm not going to say it right now for the sake of terseness, or to stay on the subject. I'm not going to diverge into that. But the double slit experiment, why is a wave or particle? I had a question. I will put it later on to John, but John may not come back again because he's retiring, going back to mountains. He's retreating. So I think he's calling it off. He's at an age that I think he's just fading off, and then he doesn't want to get into these. And he said that there won't be internet there. So in any case, but we'll try to communicate with him. But I think I have a way to analyze that. In any case, the idea is that there's a connection between physics and the IT, or what we see outside. This is another thing I'm trying to bring out here. And in subsequent papers, I will go into more details. But using these very simple things that I give here, we can convert to IT. This formula, we can convert to an IT form where you have the audio, video, image. These are the things that we see in the real things. Again,
could you
we
zoom
can
back
split.
in? Can you zoom back into the text?
Zoom back in?
Yeah.
Okay.
You're a little bit too far ahead.
How about now? Is it better?
Yeah.
Is it better? Okay.
Oh, yeah, that's better.
So now you can see better now?
Yeah.
Okay. So again, this is a 4-vector. You see that the 4-vector aspect come to so it's kind of a reflection of the 4-vector time matrix. It's a reflection of that. By using this reflection, we can actually convert to convert to an IT form like this one. I call it an IT form for making it a simple term. So essentially what I mean is that 4 vector, now you can differentiate into audio, image, video, communication. I spend a lot of time, and I have a way called operational metrics protocol where I see these things, how they play out. So I don't want to assume anything, how this play out, and it's like pieces of puzzle, how they fall. That's what I use. So it's an extra effort, difficult thing that I go through the whole day. Sometimes 24 hours, I wake up in the morning, in the sleep I see. But I think it's very important because essentially everything is an information wave I see, and the information comes in, and I try to store that information and transform that information because
yeah. So
that's what this is. That's what this is. So it comes, the information comes in a mixed form. You have audio, image, video, texting, communication. It always comes in that form, but you have to separate them. See, that's a big job our brain does. Yeah. So then it sends to audio in our brain, then it sends to the image in the brain, and it sends to a video in the brain, a texting and communication. So it all separates there. Somehow our brain has an unbelievable thing, right? Better than any supercomputer. So I see this one. Yeah, I see this information splitting into these forms, and we should not mess with that in the sense that whatever we get, we have to take. We have to take the way it is. So, and that is a little bit difficult challenge, but I think I did. I took up that, and I said that I'm not going to do anything. If I don't get anything, I'm not going to force it. I'm not going to assume anything. If it works, it works. Otherwise, it doesn't work. So eventually, I use extra. Try to understand as much creativity as possible, so that I don't. Whatever comes out, from the derivative process is what it is. But it has shown a lot of consistencies. Like I said, self-consistent physics. And recently, one thing I want to point out about time, because time is going to be the biggest challenge, I think. Like Hawking said about brief history of time, things like that. What is time? And why is time, even though all the physics did, again, we go back to time. Time is able to sustain. And I will briefly call this, I don't know who said this one. Men may come, men may go, but I go on forever. I learned this poem in high school. I don't know, it's Wordsworth or somebody like that. I don't remember who the poet was, but it's fantastic. Or Longfellow, I don't know who it was. But what it is considering is that I go on forever. Who is I in that case? I would interpret as time. So we have done a lot of things with time, clock, but the time stays. We again use the time. If I want to do this live stream, I have to worry about the time. Am I spending too much time? Am I, things like that, and we may be out. So we have to always be aware of time, and the time makes us to go other place. I may be doing all this, suddenly I have to switch off and go to other things. Take care of that, right? Our body, it's about our body itself that the time dictates that. Our birth and death, things like that. So birth to death, we are alive, we are conscious. So what is consciousness? Again, I have some input I got from here. Later on, we'll discuss that. So consciousness is, understanding. The mind is a reflection of the body. So the animals versus inorganic things. Like I said, the observer can be actually surprisingly, and Sabina Hossenfield has also mentioned this, that maybe the inorganics could be an observer also. So if you say aliens, the aliens could be inorganic, not be organic, and that could be observer. Because the idea, it goes fundamental to physics of reflection. So essentially, mind is a reflection of the body to keep the body self-sustaining. So the time has that feature of self-sustenance. Time has a feature of self-wrapping. But you'll be surprised. I said about self-consistent physics. time doesn't satisfy all the conditions of self-consistent physics. This is what I'm going to write in a paper, another paper, the observer physics. Surprisingly, time doesn't. It has a necessary condition, but it doesn't have all the satisfying conditions. Time, and that is where the quantum physics and astrophysics has these inconsistencies, because you are looking at time different way. Of course, quantum physics want to get away with time, and I can understand that. That's how, in terms of event, the reason is the time doesn't satisfy all the, like I said, self-consistent physics has to satisfy feedback circuit. It does satisfy that, but there are a couple of other conditions. The falsifiability condition from the philosophers, Kuhn or Krag or people like that, or in Popper, Cartwright, who used the toolbox idea. So I went through these philosophers a couple of years ago, and I have actually written something I had not published about the philosophers talking about physics, why the physics is has not come to a reasonable conclusion about what it is. So in any case, so the time, the falsifiability kind of predictive condition, the time has not done good job. So you have the time, you can think of there, because they're 4-vector time. So there is 2 types of time. Time that comes from the past to the present, and there's a time that comes from the future to the present. So the present actually is a mixed operator, mixed thing with the time coming from the past, intersecting with the time coming from the future. So these 2 intersections is where the present is. And so we have to talk about, that's why Einstein theory has usefulness, because it talks about word line. And I adapt that principle of word line because that's very important. The 4-vector, it does allow us that. So the 2 aspects of the time, the 4-vector, are the timeline or the time coming from the past to the future, past to the present, which keep the present actually becomes a future continuously, right? Every second it's future. What I talked 1 second ago, it was past now future. So I'm always pushing it to the future. But in any case, so it's a moving problem. It's a moving point time thing. So it's not static. I cannot say present and it will be a present all the time. So when I say now, the now becomes a future. So that's something we have to just reconcile to, and we have to adjust to that. So it's very dynamic in that situation. So this dynamicity is what creates confusion and problem for all the physics, because physics needs some variables that are constant. We can control them. We call them constants. And so people kind of have the constants all the way up to Planck constant, things like that. So that we can somehow freeze that particular time, so to say, or the event, and study them and understand the physics of it. But we have to find a way to move it, and that's always a challenge. But in any case, so I think this will help in this, because they don't assume anything. The transforms are, something that doesn't depend on the space, things like that, or mass or things like that. I think that will help. Okay. So I am talking about black box here, and how do the inverse modes, things like that. So we can use a lot of the math to actually understand, but the math should not be too complicated, I think, because we got a higher level calculus. There's a problem of singularity and all kinds of problems come. So we have to keep it the calculus very carefully, so that, because we cannot assume everything is a function. See, calculus requires a monotonic function, and that's one of the problems. So we have to use algorithms instead of just functions. So some of them are just equations, but the equations does not have inverse operation. When you do inverse operation, just x square equal to 1, I think if you invert that, the calculus cannot take, because you cannot have two values of y for one value of x. That doesn't work. So the function will not work. So we have to find a new way of doing it. So that's quite the matrix. The matrix has better way of matrix algebra. So algebra we can use. So this is the idea. So just think of this thing. I'm not going to detail, just want to give a simple thing that information splits into these forms all the time. So we have to find a way to get that from each point, so that from each point we get some information. We can split into these forms. So, but for example, it may come as a code. Let's say we are using a binary code 0, 1, 1, 1 and 0, 0, 0, 0. It comes from the space. So how do you split that into these forms? That's the big challenge. And somebody was trying to use that, but I don't think they could use that, because we need that, like SETI or anything like that that talks about aliens. We get these signals, but we split into these. We get audio vibration. We may start understanding. Is the audio, is the alien trying to speak to us? Like Alexi was trying to see some kind of weird sounds we get. Or gravitation waves, gravitation waves, or CMBR. We have two forms. See, whenever you have two forms of information, it is possible to see finally X and Y, right? If we have X and Y, it requires only two equations, which means that if you have two forms of information, we should be able to you'll be able to solve that equation, a simultaneous equation, so to say. But we are not developed the algebra to the level to do that. But I think these things will help, because we need to know all the physics. See, the mathematics cannot do anything by itself. It's just a dummy. But you have to input the physics, proper physics, for math to work. Math is a great thing. It's a logic thing that connects between things. It's an interlinking thing. That's about it. Logical interlink, I would say, in a simple way. But we need a physics input to get the proper algebra, so to say. Okay, so this is very important, and I'll talk about later on. But essentially, the idea here is that any information we get, if I'm sitting still here, I'm getting some information in my brain. Actually, that contains all this stuff. But how do I separate? Sometimes our brain has the ability to separate them, but it sees as a lot of times a mixed signal. We cannot purely separate. So there is a question of a pure and a mixed. Quantum also, quantum computing, they are talking about this also. Pure as well as a mixed thing. Pure state, so to say, or mixed state, they call it. So the wave function has both aspects. So I think we can use that, and the ket and the the bra aspect I was showing earlier, like this one. I think it can be used. This equation here I gave earlier. What was this? Yeah, this one. So this is the basic thing, and it has the power to separate, by using calibration. So we have to do some calibrations, then we can figure out how to separate them in terms of wave function. Like I said, the light is the gradient, and the sound is the curl. So using these things, we can separate them. Eventually, we should be, by using very clever methods of algorithms, we should be able to separate them. Each information point information, we convert to these things. So eventually, the code, it could be binary, it could be we may have to use more than a binary or octernary or some other type of information. So the idea eventually is that we can convert this. So I can use time and transforms. So it starts from transforms. So let's say it's the x-axis. The transforms convert to time, which is the y-axis. So there's a relationship we have established earlier with algorithm. And this time, then z-axis is the information. So by using x, y, z, normally this is the x, this is the y, and z. Remember, this is a normal lower. It's not a lowercase x, y, z, but I had to convert to capital X, capital Y, capital C, because that the capital X depends on our understanding of the physics. Only we understand, we can convert the small case X to capital case X in the bracket. So when I use the capital X, when I use these transforms here, it means I know what the physics is. Without that, I cannot do this. And the same way, time. It's a 4-vector time, 4-vector matrix. Information. The same way, information, like like these. I know how to do this. So only then I can do this. So when I use these terms, it implies these, which I will bring out in our further papers. May not be, it's implicit, it's not clear, probably it's not explicit here. But then using these, we can convert from past, present, future. Like I said, the time always, this one is keep moving, the present is keep moving. This particular interface is moving all the time to the future. So each point I look at that, each point by point. So is every point, then we can analyze. So it's a huge database we'll have, but I think there is a way to simplify that. And we can see is each point as a different past or a different present, a different future. So in that case, Einstein may be correct about some other things he's talking about the clocks and gravity. So that's the idea here. So I can use that, eventually convert. I use in the PowerPoint presentation, I gave about Feynman diagram. And I said that the Feynman diagram, for example, I'm not going to put it now. I just show it here briefly, if you can see. So I have electron, positron, right? Feynman diagram. And then I have a light, a gamma, which converts to quark and
no, I can't see that, Rajan. What are you pointing at?
Oh, okay. So let me pull the PowerPoint presentation. Maybe it's a good thing. I'm trying to avoid that, but I think it's better that let me see. So I had to now change the screen to that. Let me see. So let me stop sharing, and then I have to do present again and share screen. PowerPoint presentation. Where is it? PowerPoint presentation. Oh, I had to use window. I think it's in one of the windows. Yeah, I think I can use that. Let me see. Let me tell you. Can you see now the share?
Oh, wait a second. Yeah, I'll have to exit.
Oh, okay. Oh, each time you have to. Okay.
Yeah, I have to. There we go. Sorry.
Oh, can you see it now?
Yeah.
Yes, thank you.
Oh, you can see. Okay. So this is what I presented in the PowerPoint, if you remember.
Oh, I remember. Yeah. We saw this last week.
Okay.
Previous week.
Yeah, I talk about geometry of space. Another paper. So in that paper, I said that we can retrofit Feynman diagram with this wave function. This phi actually can be eventually phase angle, but I'm sorry. Actually, what I meant is a scalar potential. Actually, scalar potential that I'm talking about is gauge potential is what phi is, but it can be converted to phase angle and the Q factor. That's what I want to do later on. That Gerd was talking about. Convert that. So this it's one of the most fundamental things. And I remember that even Wilczek, the Nobel laureate, and a few other people signed, they thanked Feynman, saying that it's the most fundamental thing is diagram, because it helped them to calculate everything they want to calculate. I think even Higgs was saying that. So I do believe in that, but there are some modifications we have to do. We have to take with a pinch of salt. There are some problems with that. As we know from quantum, in general, quantum physics or relativity physics has some problems associated with them. So I think we can resolve them, the standard model and all that. So say electrons. This is a Feynman diagram I pulled out, the normal Wikipedia, or I used one of the paper people who had written fundamental quantum physics from Feynman. So I saw this also there. So that's how I pulled out. I think it's a normal thing, right? Everybody knows this one. So it's
what is it trying to get across? It's positron. Or,
this is electron here, right? So what Feynman was saying that
but it turns into a photon, then it turns into a quark and an anti-quark.
In the light,
So quarks can't exist by themselves, so it must be what?
It evaporates. It evaporates. There's some description. If you go to the Wikipedia, it says that how it converts from electron to positron. There's a simple one paragraph explanation of this one. I think I have put it somewhere, but I don't want to.
Well, I mean, time is going across.
Time. With time. So it's an interesting thing.
So it's saying that a positron and an electron are annihilating to form a photon.
Annihilating,
which then converts back into a quark and an anti-quark with a gluon spinning off it. But that would just be what? Some level of a diagram, like first level or second level, maybe.
It's actually a first level. People are used. You are like hundreds or thousands of diagrams, Feynman diagrams. People are used, right? The standard model and everything to describe everything, all the particles. So they are do for each particle. They will do this.
But does that mean? But there are certain rules involved, are there not?
There are rules. No, they do calculation. You have to. There is a calculation involved and also a experimental proof. I don't know how much they had done that, but a lot of the things in the LHC, for example, right? They had to do this. They use this and use a calculation and then actually determine from the spectroscopy whatever you get from LHC measurements. They will see how much does it conform to 1 sigma level, 3 sigma level, like Higgs boson. They saw it at the 4 sigma, I don't remember, 4 sigma level or something. So they try to fit in with the experimental statistical data and see how the prediction is going, whether that's occurring in that spectrum or not. So these are the very tedious calculations they go through, right? But use this is the fundamental thing they use. One of the fundamental things. Feynman diagram is one of the most fundamental things, right? They use graphical thing, which gives the process, which gives how the process is going on. So this gamma, which is the light, is the mediation. So they annihilate and they produce eventually light that evaporate, converts anti-quark. So many things are going on there. But then a gluon, eventually produces out of this evaporation process and all those things. And I think it's an evaporation condensation process, which produces all these kinds of particles. But I am saying that how does the electron and positron come into picture? So I can retrofit the wave function. The wave function and the scalar field is going to determine that. And I have algorithm for this now. So we can adjust the calculations using these. So I have now generalized not electron xi-phi instead of electron, I say X, just capital X, capital Y, anything, could be anything. And if it is valid, and then any field like some environment, could be light or anything, and that converts to Y prime, X prime, Y prime. It could be anything. It could be anti-quark or some other things. So I generalize this one using this algorithm. I can generalize, and that's what I'm doing right now. I think it's working out fine.
Yeah. So, is it the idea in the standard model that there's certain rules, like for instance that like a quark can interact with a photon because of the electric charge, or quarks and electrons can interact because of electron charge. But gluons don't have an electric charge, do they? So they might have color. They might have color charge. Is that how they interact with the quantum?
I will write something, and after that I publish a brief thing. Then Christopher, we can work together because you have done a lot more on that, on the geometry and the particles. So I want to collaborate with you. And also later on, GERD, I want to convert this to Q factor, and then maybe I may have GERD. And then Christian, iSpace, I have another one with iSpace, because they don't disappear. See, the thing is that why we can prove why there is a antimatter matter asymmetry. Why is there has to be, right? Because that's one of the problems, because they annihilate totally, there won't be any universe, right? But we have universe, we have matter. So how does that come into picture? And they talk about neutrino and all those stuff, but how do they come into picture? And I have developed something called E-circuit. Again, that comes from my operation matrix protocol. That's again an abstract thing, abstract mathematics, but I think it's working out. I call it E-circuit. E-circuit is like a PDP circuit. Not all of my E-circuit, like our PDP circuit, hot PDP circuit, I call it. It's an E-circuit. E-circuit has a special property that it destroys, you construct that, it constructs that, but when it destroys, it leaves behind, called retention. And I can, I studied what you call physical metallurgy. So we have one of the fundamentals of physical metallurgy is you convert austenite. You may have heard of austenite, a phase called austenite. It's a very short phase. Yeah, phase. It's a all huge thing. Okay, it's called ternary phase diagram, things like that. So, but I had to do it because I major in metallurgy to all the way to my PhD level, right? I had done that. So I had to do the ultimate, the highest level physical metallurgy. And my professor was one of the first ones. He's the original in saying what happens in the austenite matrix side. See, when you have just any structure, like you make ships or anything like that, right? You have to have hard phase also, like steel. Like it should have a structure that can withstand, right, all the forces of nature. So if you use austenitic phase, just think of it's a phonetic. I'm just giving you. It's a soft phase. So suppose I'm using sand, right? I cannot build a house. I had to convert with cement and make into hard concrete, right? To make into a proper structure, because you have to withstand the forces of nature. To be, even up to tornado. I mean, of course, tornado destroy, but normal forces of nature, rain and sun and all those things. So they have to withstand that. So we convert this sand using cement and everything. Cement is like a glue on, right? So we use that, and then we use probably some kind of rocks or pellets or rock pieces. So we put them together and make into concrete, and then concrete sets. The concrete sets, then we have a strong structure. We can build strong structures. That's how many other structures are built. And iron is very similar. So iron is you can heat it up and called blast furnace, and then use different type of steel processing furnaces like Bessemer process, different processes there. So what happens there? We can use something called phase transition. It's called TTT, called time temperature transformation. That's one of the fundamental graphic that's used. Also do calculations, and that gives a map of what phases occur at different temperatures at different times and how we can convert. So if you have soft phase like austenite, like I just, it's a lot of description. I'm just going to simplify that. Let's say that's one of the soft phases, and you convert a hard phase like concrete, right? From loose soil to, so austenite is like a loose soil, to give a brief analogy. Actually, I can talk about, because I had done the highest level metallurgy, so I am fairly, I'm now not an expert in that because I have pulled away from it, but I would have been, a professor in that. I have taught a little bit on that physical metallurgy as adjunct professor in one of the universities here. But now, if I re-understand from physics does clear a lot of things. So I like physics because of that. So the physical metallurgy.
A bit of also with chocolate, it's there's different kinds of chocolate that have different melting points as well. It's based on the type of sugar you use, whether it's very granular or more coarse.
Exactly. Yeah, that's excellent analogy, Christopher. So same way with our water. See, water, what happens is water, goes through different phases, right? There's a vapor phase, there is a solid phase, which is called ice. And ice has a very, I was enamored when I studied in middle school about anomalous expansion of water. We call it anomalous expansion. When water cools down, you will expect from the normal thing that solid is denser than liquid, right? But the ice is very strange. The ice actually is lighter than water. So that's why it floats, and that's very critical for life to exist, because in the North Pole, things like that, you form the ice and that insulates the underneath water. So all the fishes, all the other organisms can live. Otherwise, everything will be just one icy mess in the universe. And you mentioned about cosmic ice. I kind of briefly, I had to go into more details. Quite interesting, Christopher, about the cosmic ice. Of course, that theory, is debunked. It's not a perfect theory, but it gives an idea about our own Earth, how Earth could have formed, sustained life, and things like that. And it's a very important thing, right? Sustenance for life, because that ice covers and forms glacier and things like that. But the ice sheet insulates further cooling, insulates the water underneath, so it keeps it warm. So like 4 degrees C is the densest form of water, I think. And then of course we use carbon dioxide, things like that. We can change that So you see the phase transition there. The phase transition. Same thing happens with metals also. When they go through phase transition. Similar thing.
So, pressure and temperature, isn't it? So you can have
exactly
liquid metal, and gaseous, or well, I assume we'll go into more like plasma or something at a certain point.
Exactly. We are at least 4 phases we know. There may be a 5th one. People are saying there may be 5th one. Right now we know gas, liquid, solid, and plasma, but there may be a 5th one also. They say.
What about superfluid? Is that a different phase?
It could be superfluid. You are right, Christopher. It could be the superfluid. That's a 5th phase. That makes sense to me.
Well, I mean, then if they're saying there's 5, they're not including superfluids, then that would mean that there's a 6th one that they're interested in. Or do you think that maybe superfluid?
I think the 5th phase, I would think as superfluid may be a better one. That I think in terms of these, if you have gas, liquid, solid, and plasma and superfluid, I think we should be able to explain everything. We don't want to add too many, right? We want the minimum number.
Yeah, exactly. I mean, superfluid seems like a very special case anyway.
That seems perfect.
Why shouldn't it exist in nature in some sense? And if it does, then I mean, it exists in a lab. So.
The reason is, like I said before, the superfluid is not visible, right? It's superluminous and the monopoles and things like that, but it's not visible. So it's like a dark matter or dark energy, whatever you call it. So we cannot see it, but we can see liquids. We cannot actually see air, for example, right? The gases, but if we use color, some things we can make it visible, right? We can use colors. We can use some chemical thing. We can see the gases, scintillation chamber, things like that are examples. And then we can see liquid and solid, depending on the refractive index, right? So it's all relative aspects. Refractive index is the most important thing. So maybe if we think about refractive index of the superfluid, and we can find the refractive index of the superfluid somehow, if we can calculate, we can prove why we cannot see it.
Okay.
It's like Invisible Man. There's a famous book I read in the school when I was something called Invisible Man, and they talk about refractive index, like like
You could have a
glass.
negative refractive index where
Yeah,
the
yeah, it
light
could
curls.
be. Yeah, if we can calculate that, that is fantastic. It will be almost like a Nobel, or we can publish a paper. I think it's possible to calculate. GERD is good, GERD has, I think it's in that line, and Christian also probably is in that, and you also.
Yeah, for sure.
Yeah, so we cannot work together to do. I'd be quite interested in finding refractive index of superfluid. That is one paper by itself. If you can calculate from fundamental physics, that'd be a fantastic thing. I think that will prove why they could that and then you can say, okay, dark matter is because they are dark because their refractive index is negative, like you said, or something like that. So then we can never see a dark matter. But plasma, for example, plasma, again, the sun and everything we see in the star systems mostly are plasmatic, right? Phase. So they are ionized forms. Ionized form, they exist only in ionized form. So the plasma.
Well, there's some people thinking that Robert Bataille says that maybe the sun is a liquid.
Oh, yeah.
Because I think you could have like helium at a certain temperature, but also at a certain pressure, or hydrogen, which are, I suppose the more abundant chemical is hydrogen, maybe helium.
Oh, yeah.
And then, but if it's at a certain pressure, it could be a liquid as well. That's his
yeah, definitely. See, thermodynamics, I did fairly high, one of the highest level physics, thermodynamics. So I would have been I would have physical metrologist or thermodynamics if given, but I got attached to physics. From my school days. So that's when I think physics explains, it clears a lot of things. So which thermodynamics can use eventually and things like that. They are not a perfect science, but I think physics is more perfect science. But of course, there are problems, physics also. But the question is observer problem. So that's where we are trying to solve. But the question is, there's something called Le Chatelier principle, chemical thermodynamics. That I love that, because it says that when you apply, one side of the equation is the reactants, the other side is the products, right? So Le Chatelier's principle is that based on the pressure, temperature, and composition, we can push the reactant to the product side by adjusting these things, and it gives a nice equation. Gives isotherm and things like that. And the Le Chatelier also, along with the I think Helmholtz and people like that, they together have an equation. It's a nice equation which tells when you apply certain pressure and temperature, how that phase becomes that phase. There's a thermodynamic equation expression. Yeah, that gives perfectly how to calculation of that. We apply if we apply pressure and temperature to water, you can convert to ice, solid ice, things like that. So yeah, you are correct. Same way, superfluids. If you change this, that's the environment. I call the environmental parameters. So if you change the environment, we can change the system. So thermodynamics talks about the system. There's local system, global system, but anything can be controlled. Like you see, the fundamental principle of the thermodynamics. About the Carnot cycle, right? It says that you cannot get 100% efficiency. It has to be less than, because it's T2 minus T1 over T2. Delta T over T2, which is the in absolute values of the source temperature, something like that. So we cannot get 100%. You can prove it from there that we cannot get 100% efficiency, because we have to keep the absolute zero to get to 1. T2. So T1 has to be, capital T1 has to be 0 in order to get 1 or 100% efficiency, which is not achievable yet. Yeah. So it has to be less than 100%. So that's why you cannot have perpetual motion machine, for example. And it proves Carnot cycle, calculations show that why you cannot have perpetual thing. But I believe the universe is a perpetual, because it can keep absolute zero at some point.
Oh, okay. So this is the whole point in the PDP circuit.
Yeah.
Goes around.
Yeah,
Yeah,
that's a PDP circuit.
Oh, right. So will we go back
Excellent.
to the other paper now, or the...
Yeah, I will go back there. So
Okay.
I just want to briefly explain this.
Yeah.
And I will stop sharing this one and go back there. So that's
then
off
I'll-
now, right? So now
Yeah.
I'll go back and share screen. I think I'm getting used to it slowly. It takes a while to really do it in a nice fashion. Let me see, go back to...
I've yet to present anything, so I don't know what it's like. So.
Is it coming now? Oh, sorry,
Yeah.
I'm presenting the wrong one. No, this is where the actual thing is, but you know, the actual paper is okay. So
very
this is
good.
where it shows the research model. If you go to that website of the research journal, it shows that, and I think it appears in the current issue. Or only my paper is published so far in that one. They may add something more, but my paper is the only one, the first one, and I had to go to PDF to show that. Okay, that's the paper. I'm not only me. I wrote the thing, but they have edited and they have added some things. Manuel Emery, and then Christopher. Originally, I wanted him, but he said he want to do it later on. So I think it's a good idea what Christopher was saying. But so I'll have a brief publication like this, and then we can add on, because that helps us to understand what's going on. The paper is a self-consistent thing, I think, trying to be, because like you mentioned, this has more ideas, but I want to separate it so that it presents only one idea in one paper, and then it gives the whole detail for that. Yeah, I want to do that eventually. I think that's a good idea, Christopher. You have told me. I'll follow that.
I think so. If you have a lot of different concepts that you're working on, way like in string theory, they're at such a complicated level that they're talking about, relativistic fields and quantum mechanics and different dimensions. So it's complicated. So it's interesting, but it's still in one area, which is string theory. So.
Oh yeah, exactly. So I want to break that into simpler, smaller papers that gives one idea each one. It just says that. So I think it's nice. I mean, that's conforming to this idea of separating the information into these multimedia thing, separate multi. So eventually what I'm saying is that going to the details of the physics, that's where the physics is useful. We can use this one to get this one point to point and understand, and hopefully eventually decode the signal that we get, in terms of 0, 1, 1, 1, 1, 0, 0, 0, whatever it is, a matrix of signals that from outer space. And we convert this one, convert this like this and this one. I think we have a better way of understanding is the aliens there, or what's happening, things like that.
Okay,
so,
I had a couple of kind of questions or maybe comments or something. So, so if you think about physics is like study of objective physical reality, kind of.
Yeah.
And then, what I'm thinking is you are looking at reality from a kind of a subjective reality, in a sense. Like our perception of reality could be broken down into things like audio, visual, thought, even, and that's our sort of internal. So, then we ask, like, can physics be used to explain the baseline of our perceptual experience of reality? This one seems like that's the kind of question you're asking. And this is so as a kind of a holistic idea or even metaphysical. So you know what I mean?
Yeah, like ontology.
I used to think about physics like on those terms, like as well. So that's why I think I understand where you come from. So like, you could split it then, saying physics is materialistic and reductive, whereas you're more maybe holistic in that sense and more metaphysical, would you say?
Yeah, and also ontology, like ontology, things like that are there. And there are different thoughts in philosophy that some of it I know.
Ontology in terms of like categorizing things and their connections to each
Yeah,
other.
categories. Yes, exactly. So I want to categorize things and like sorting out things, you know.
Oh yeah, that's cool. But like all of those things are being done in the human mind as well. So
Yeah,
right. So I mean, it's a very mental process.
mental, yeah, mental process.
You know, and so if those mental processes underpin, or those kind of
Exactly.
processes underpin reality, then that suggests again a more physical, almost like there's some sort of mind underlying everything.
Yeah.
So they're interesting ideas. So I think you seem to be kind of mixing hard scientific maths with sort of very difficult metaphysical concepts and trying to join the two of them together, which is like, it's never been done before.
Oh yeah, thanks. Yeah, yeah, it's a difficult thing. Yes.
Yeah. So yeah, it's
because
pretty.
Yeah. See, in between the 90s, early 90s, I had like a vision, like a revelation type thing, because I went to actually, I was in a like a tubing type thing. It's called tubing here. So it's like you are, you know, in a freestyle with some friends I went, but you are by yourself.
Okay, yeah. It's like a water thing.
Yeah, I got drowned in that. It was a huge stream which has vortexes. That's why vortex thing comes back to me. So I was drowned, I would have been dead, you know. But I waved my hand up in the air, oh God, before I went inside drowned. But I am totally unconscious. But somebody from the shore, very good swimmer, saw me, a couple of swimmers, they came and rescued me and put me in the helicopter, things like that, and rescued me to the hospital. And so I was revived. They gave me CPR because, you know,
So
I came back to life. I was dead, then came back to life, you know.
And how did you, do you have any memory of
so I wrote, so immediately a lot of things happened. So I started writing. So I have written, you know, a lot of information comes so fast, but I you know, my hand goes like a printer, you know, so fast printer. And I written my experience with life. I have actually somewhere I have sent to a few people, like, including my professor.
So a lot of those ideas then are sort
of it came from that's a metaphysics. So I started not from physics first, metaphysics first, and then converted into physics, you know.
Yeah, that makes sense. So you're trying to convert these metaphysical ideas into mathematics, sort of.
Yeah, exactly.
Yeah, okay. So that's why the work is the way it is. Yeah, because like if we look at science, would examine the brain and the experience of our minds in terms of neuroscience, you know, so neurons firing and electrochemical things. So you're kind of bypassing that almost. If you're doing what I think you're doing, you're looking at it from a metaphysical point of view, arising from physical concepts, or the other way around. So this would imply that you belong to this sort of Plato's caves sort of school of simulation theory. So do you believe that the universe is a simulation and that our minds, our fleshy minds, are not real?
Yeah.
In that sense. So there wouldn't be any reason to explain it from a biological point of view. You're looking at it purely from a energy point of view. Is that it?
Well, the aspect is that I think it's more fundamental than even energy. I had partly agree with John about that. Energy is created some problem, but energy is a burden. I think it's a force field. We have to understand what kind of vibration.
Right. So you're not just to be clear, you're not saying that it's that the world is a simulation, or that it's not like it, you know, a Maya kind of some dream state kind of thing. Or are you trying to find the physics of dreams? Essentially?
It's essentially a vibrational discontinuum. If you see a vibrational discontinuum from superfluid, if you want to talk about that, you know,
so
the fifth phase,
So the physical thing then that's underlying our perception.
Underlying thing, but is it organic? That's an excellent question. Is that consciousness organic or inorganic or both? That's a big question.
Or neither.
No, or neither. Yeah.
Yeah.
So you have multiple choice. Multiple choice. Which one is the correct answer there? You know. So you have like
Well,
4 choices.
yeah, I mean, it can only be organic or inorganic, right? Those are
Yeah.
Well, unless no, but I mean, well, that depends. You're talking about chemistry at that point. If it's not chemical, it's not doesn't.
Yeah.
Well, if the rules of chemistry don't apply to it, then it could be neither, right, or neither.
Yeah, exactly.
Yeah,
So
so that's why
legal-
I said that. Yeah, so like if we were talking about pure energy, that's not chemical. Then it would be
Mhm.
it wouldn't fall into that category. If it was quantum, even then it's not chemical. I suppose it
Yeah.
would still be called inorganic in some sense. Well, it's
This is
interesting.
when yeah.
Well, you're
This is when
talking, you're talking about aliens a lot there, Rajan. Oh crap! Sorry, hang on a sec. I just opened something I wasn't meant to.
Okay.
I'll quit that because I don't want my computer
Oh,
exploding.
you want to share something? Should I get off?
No, I just want to make a
Okay.
point
Okay.
that so you're talking, yeah, about the alien kind of question, because I didn't make any notes about this, so I'll have to just go off the cuff. That's fine. But remember, I was talking the guy who invented category theory. No, he didn't invent it. He did a lot of work on it, though. A guy called Grothendieck. Yeah, we were talking about him before. And
How
so
can you send me?
I'll do my best. Yeah. I'll
Okay,
look
thank
up.
you.
So Grothendieck is he popularized category theory, especially as a means of explaining how the universe came into being, or how we can describe what we see in the universe. And then towards the end of his life, I don't think he's alive. Maybe he is still. But yeah, as he aged, he went into sort of exile up in the mountains, a bit like John, and but in a different way. He was living in a community like of people in Italy up the mountains, and they were kind of looking after him. But one of the things he did was like eat dandelion soup, because that was what he had to eat, and he got obsessed with this idea that the universe was being manipulated by aliens outside of our reality, who were kind of outside of reality. They were able to control time and events by altering the speed of light slightly. So pretty out there kind of theory for someone who was the pioneer of like category theory and all that. But I like those kind of theories. So recently I had a dream about the beginning of the universe. And so this was what I learned from the dream. So it's going to. So basically, at the singularity of the universe, there's a lot of matter compressed. And that's obviously, let's say space expands a little bit around that, because, we go with expansion theory. And there's going to be and then all the matter is still, mostly compressed, let's say. There's going to be, well, I suppose it depends on how you, because does the matter spread out with the space as the space expands? I guess that is correct. But like, if we just look at it in this simpler way, there's like going to be a huge, well, even if that is the case, there's still going to be dense amounts of matter in there. And so you're going to have extreme gravitational fields, which would affect time. Assuming like time, the clock is running now because the universe has started. But because time is running so slowly, you could have like a very large amount of events happening in there. So anyway, in the dream, there were these creatures that like existed at that point, like at the point of creation, because like everything comes into creation at the start. So it was like reasonable for them also to be created. That's what I'm trying to say. They could be, the universe could be created, so could these things at the same time. So, and what they did, because time was going so slowly, they were able to move and do a lot of stuff in a very short period of time. Was the kind of a concept. So that might be a bit logically inconsistent, but basically they kind of created everything in the universe, just like the way birds flying through the air have like certain patterns, song patterns. They also have like these patterns, and they sort of organize everything in the way that it is, just by their own activities, natural sort of activities. So that was the idea. I thought it was kind of interesting. So they could be Grothendieck's creatures that are manipulating the speed of light. They're cool. In the dream, they're called the Dien Lear. Yeah, I don't know. It's just a weird dream anyway.
Okay.
So that was it. Those are my questions. I suppose you were talking about the CMBR as well. You don't think there's? Do you think there's information stored in that?
Yeah, I think they carry our astrophysical information. I think the CMBR and also gravitational wave, they carry the information, and the
Yeah.
information, if we can delineate that or discriminate that, whatever you call it, differentiate that into these forms, right? Audio, this thing. That's what I'm trying to say. Each point, we can see whether it's a living or a manipulative thing like an alien, or is it's just an inorganic interactive.
When you're talking about audio there, Rajan, you know, when you were saying we can see air through different spectrographics, and then you could take like, for instance, with the that thin ice monotonic monopoles, where you could they could listen to the sound of the magnetic field.
Yeah.
Remember?
Yeah.
So is that what you're talking about? Like, so like audio in the sense of like converting the electromagnetic signal into audio.
Yeah.
Okay, so
so the vibration information is very important, right? For life, if you want to see life existing, like somebody from here, say there are aliens, I'm not sure whether they're or not, and they're looking at our Earth, right? They'll let's say they have this advanced way of figuring out, separating this and finding audio. They'll find the vibration of life that we have. We call love. It's actually a vibration of life, right? If you invert that, if you do anagrammatic, phonetic anagrammatic operation, we can see, if you do the thing, we can actually prove love is actually a vibration of life. Okay.
What is what is a vibration?
Vibration of life is love. L-O-V-E. Love.
L-O-V. Oh, love, right.
Love.
Okay.
So
gotcha.
If you rotate that V at the point and use a rotational, right? Like a rotation, we can see that's vibration of life. So, you know, people are not. So it's a vibration of life, you know. So that's a self-sustaining aspect of life.
Yeah. Okay. That's properly metaphysical as well.
Yeah, it's metaphysical. Yeah. So I did a lot of these kinds of what you call informational processing type of thing, you know. That helped me actually. Yeah, with analogy.
Code within the system of language as well.
And
I have a question.
Yeah.
Oh yeah. So have you heard of the axis of evil? It's a terrible name. But...
Oh yeah, that's why I said evil twin. Remember? I should actually find out. I couldn't. Yeah, I should actually pull out a video. It's a very interesting thing about evil twin, the quantum mechanics of that. Just proved with some experiments, like double slit, very similar to double slit. Yes.
Right. I don't know about that at all. Yeah, you'd have to explain that to me or send me.
But I would say one of the things I'm thinking about it again, later papers, I think I will analyze that. I think it's a parity difference. See, everything is like copy. Suppose you have a twin, right? Twin is like a copy of the other twin, right? The only difference is parity. The parity is the only difference. So between God and devil, the only difference, you can say God and devil. That
parity is in the sign, like plus or minus.
Yeah, plus or minus. Parity could be that. But like Bender, people like that have Carl Bender or somebody. He has actually go into detail about parity. You know, about
so good
parity.
And evil, left and right.
Yeah.
Parities. Yeah. Okay.
T equal to 1, T equal to -1, things like that. He has done very detailed, and he goes all the way to Riemann sheet, things like that, at the Planck level to analyze that, how the parity changes. So the parity change is the one that changes the phase, probably. So superfluid, you can actually prove maybe from superfluid to the real matter or particle, maybe it's the parity that is changing, you know. That creates eventually even charge and time reversal mechanism, things like that. So CPT is a very important thing.
Well,
you know,
I think, you know, the axis of evil is about how what is this? The CMB is aligned along the plane of the ecliptic.
Yeah.
Something. Yeah.
So you have different axes.
To be like aligned with the entire universe.
Yeah.
Which is
like
interesting. Robert Patel says that perhaps the entire reading of the CMB or is incorrect, and that they're just reading the electromagnetic spectrum of the sea. It seems a bit odd because like some of these satellites are way out in space, are they? But I think he was saying that they were saying that one of them was around a Lagrange point, and then apparently he said that it wasn't. So he was saying that they were lying, which is a bit strange that you know, like a company like NASA would say. But I haven't really researched that, so I might be incorrect on that. So, but the yeah, so I'm not sure if I agree with Robert's Patel's view on that it is the sea. I thought it was interesting when I first read it, but I mean, yeah, would that even explain why there's a that it's aligned with the plane of the ecliptic, or is it it's aligned with something anyway? It's not the equator, but it's I think it's the plane of the ecliptic. So, but that just kind of feed in with some of my research. I might do a presentation on that, and and then next week I'll when I'm speaking off the cuff, I could get details wrong, so you no need to do
great.
that.
That will be fantastic.
Yeah, cool. So I need to know that. Cool. So there was another thing we were talking about last week about how, you know, the curl of the magnetic field, which when you're decomposing that from the gradient. So you have the gradient and the curl, and then you decompose them and say they're two unparticles, but really they're just one particle, aren't they? So you can recompose them, and then you kind of just have two particles, which is a positron and an electron. Is that correct?
Yeah. More like light and sound, actually. More like photon or phone. Light and sound. Like
phonon is
not phonon. Light and sound. Light and sound.
Right.
Let's say light.
Yeah, but okay. Well, we were talking about earlier the sounds. Yeah, no. Well, I'm just speculating on that. But if we were looking at something's rotating clockwise, from one point. But if you go around and look at it from the other side, it's rotating anti-clockwise. We were talking about this last week, I think.
Yeah.
And Christian had a very interesting experiment that he was talking about, where there was some sort of thin rod of metal that was vibrating like this.
That is not yet in the works. Sorry, guys, this will be deferred, but I'm working on a 3D printer and stuff to do that on a more professional level. With the loop-based stuff, it was not manageable, unfortunately.
Are you saying that research hasn't been published yet?
No. This is just something is on my mind a long time, and I wanted to verify or falsify it, more or less for the sake of research. I don't care if it works or not. I just wanted personally to know. And to find out, you need to do a quite high precision level. We're talking not about in a millimeter, but less, and it's just extremely precise, or it won't work. And
are you able to do that like in a lab?
Yeah, with a 3D printer, I am.
Right, great. So can you print on the atomic level or something? Or?
No, it's just the mechanics of these things, rotational wise and stuff, and precision of arrangements needs to be exact enough to give any conclusion about that, what I want to know. So as I always mentioned with John, you cannot just put kitchen magnets and attach them together. So on this level, you get something, but not a conclusive yes or no for the level of question I'm after.
Okay, right. Well, so this research has been published, so I can talk about it, yeah?
No, not been published. Not been published.
No, the other, the original thing with the iron rod that goes up and down. It wasn't iron. It was made of.
No. I remember what you mean. Of course, that is more than published. But this is, of course, nothing to do with mine. This is the quantum experiment, which shows that the mechanical object, in the sense, is a quantum mechanical object from the size, a nanometer style object in a semiconductor, is in superposition with an oscillator, an external one, is part of the chip, but is millimeters away from the thing, in the sense from a speed of light distance on the chip quite far away. It's not near in any way close. This could be even on a separate chip with wires, but they managed to manufacture it on the same chip. And so with the magnetics and the mechanics necessary to get this thing into superposition, which is difficult enough from what I learned with these kind of experiments, multi-Tesla magnets and stuff like that, which you need in quantum Hall effect research. But they all have that in a typical Siemens standard labs. And what they managed to do is to show that the resonance of the wave is a force. So the electric wave induces a force into the mechanical stick, the rod, which is a quantum rod with a quantum ball. The name is literally a ball. They etch it out of the chip in multiple layers. This is a combination of production mechanism, if I understood that right, from standard chip semiconductoring and electron crystal. This is aberration by electron. What is the tool? I forget what the tool is. It's not the microscope. It's an electron chip manufacturing thing where you can do prototypes. So where the electron beam hits, the atoms are extinct out of the substrate and the upper level. So you put a level of fluid, dry that, and then the electron beam rides over it and makes it a structure. And the next level, like a 3D printer, essentially, is a very slow process. But prototype means stuff-wise, you can create structures which are free. You know, normal 3D printer has the same problem. When you have a standard 3D printer, you need some helper materials to get things which hang over, because otherwise the heat stuff would melt and then would bend away. Or so it's the same. You cannot just easily put 3D structures into a chip. Current chip manufacturing can do much more, because at Intel I know of a process from Harvard where they vertical put the transistors. Now a standard process, but 10 years ago it was absolute top of the notch technology, where the transistors are not horizontal welded over the NP gates, but vertical. And when you put them vertical, they become very small from the Z-axis view, and you get much more transistors per square meter on the grid. So, but these kind of technologies are able to three-dimensional sort of attach things that you can create a rod, which is quite long. They said nanometers. I have no exact numbers. I put to find the paper. But what they managed is to bring the rod with a piezo element to some swing, and the piezo element is an electrical thing, got the resonance frequency coupled with that resonance wave generator, and then they put the wave generator into superposition. And what they could experimentally see is that then the rod, so this is not touch the rod, but I don't know this, they had a normal gamma photons, I think, what they radiated off the thing, and it showed that the thing was both up and down at the same time. Mechanically.
Amazing. So it's not because it's like vibrating so fast that it
nothing like to do with that. It's really at both positions at the same time at a time. Normally when it's vibrating, you have a film in your high-speed camera. You can see, but like any child does it in school, when you have a ruler and the ruler is long and you make it swing and you touch it up, the frequency goes up. It's like, and the standard effect when you shift the ruler up to the table, the frequency raises until the resonance is completely damped and the ruler is still a ruler. But when you have a small, what's that, Riga in English? I don't know the word. So when you have a small tap, like on the bridge, when the soldiers walk over a bridge, you can make the bridge swing. And it has eigenfrequencies. And within these eigenfrequencies, the resonance frequency, when you hit it, you can make even the biggest object very easily swing and get destroyed.
Sympathetic resonance is another, perhaps.
And so they needed only super small forces to get this very light, couple of thousand atoms long, I think, stick to get into swinging. But if you have a camera which is fast enough or synchronized to the point, and you see that the stick is always like when you flash at it and at a lower or upper position, okay? And this is what you expect. This is the control experiment. When you're not in superposition, you see that the thing is either down or up or in the center or wherever your stroboscopic effect will photograph it. And once they're in superposition, the stroboscopic photo show this in both positions at the same time. This cannot be, but it is.
Well, what if it was connected to, I hate to say, you know, the time reversal invariance, or they're also not retroactive causality, but time reversal invariance, you know, that like you play something one way and it looks the same as when you play it the other way. So when the stick is going down, it looks the same as when it's going up. So it is up and down at the same time. Did that have something to do with it, do you think? Or?
I cannot comment on the idea. I have only read the paper. I still have it somewhere in my hard disk. I would wish I would find it easily. But if you tell me I should search it until next week, then I do that and post it for you before if I can.
Okay, yeah. Well, no problem. I could even probably find that online. I think that's quite a big experiment, I can imagine.
This was presented in a live audience after they made it, and I heard just from the resonance of that they got standing applause from 4,000 people in the room or something.
Yeah.
So okay. I hope that they knew what they did. Because that is really weird. One should not lightheartedly say we saw mechanical resonance of a quantum-sized entity swinging in coherence with an entangled wave. And entanglement in everyday life is already weird enough, right? So I have friends in physics who know people in the University of Vienna. The University of Vienna is the one which got the Nobel for the quantum teleportation and these kind of things. And that is not so weird, but one of the most weird experiments I know in quantum era is from Walter Hensch, but also a Nobel for that is a quantum eraser. It shouldn't work that way, but it does. This experimental proof that quantum mechanics is at least real when you measure it, not real from a... And be careful what I say, huh? But you cannot negate if I said quantum mechanics is shit, we replace it with something else, because this is seemingly what nature is actually doing. So an interference of elements over large distance, like the prominent example going over the Canary Islands, 350 kilometers, they make entanglement over lasers from island to island over a telescope. And you see the quantum effects, which shouldn't be, because speed of light should be limited to c, and the distance is high enough to guarantee that within the reaction time of the sensors on the emitters and the receivers of this cryptographic entangled transmission line. Yeah, I think I saw it in a paper that the Chinese did it over a satellite in space. So they, if right, they increased the space to a geostationary satellite to then about 120,000 kilometers to 64,000 up and down. Yeah. And could reproduce it. Well, there was a paper, I haven't read it, you just see the abstract.
Okay, but isn't there...
Let's assume for a moment that it really works, then of course superluminal effects could be an alternative equation. If going back in time is a probable explanation geometrically for such effects, is a matter of if you invent a proper geometry. I can give you an example what I came up with a long time ago when I was thinking how the hell these EPR experiments could work. I just wanted a mechanical explanation, like a clockworker who disassembles a clock and said, now show me the gear. Yeah. In quantum mechanics, you're not allowed to ask, show me the gear. If you ask that to an ordinary professor, he will tell you, shut up and calculate, because that was Feynman written in his books. And this is the answer you get. It's still as of today. I don't like the answer, so I'm still the boy wanting to open the clock and look at it. And it's fair to ask. You should just stay the boy and ask questions. Questions are the actual clever ones. The answers are not even so important. The questions are the cleverness. You ask a clever question, you make other people think, and that changes something.
Yeah.
And
well, with
there might be multiple answers correct to a question, and I have not borrowed the truth. So, but what I did is, if you have magnets and put a piece of paper and make a line with an x-axis and an y-axis and put them folded exactly at the y-axis, and say that would be a mirrored space by design, like an I space, whereas at the x direction would have an anti-x, y would have anti-y, and so on, what I explained in my video. And this is a hypothetical 6-dimensional space, fine with that. So what can you do with it? So when you have x and anti-x, and the particle would be entangled between x and anti-x, because they would be essentially the same. They would travel x and anti-x at the same time, because on a thin layer between x and anti-x, they could communicate via gravity, via whatever information, because x and anti-x is not necessarily far away. It could be in the nanospace, the same space even, entangled.
Yeah.
And when then something travels to the right, 200 kilometers, and something to the left, 200 kilometers, it actually travels to the right and the left at the same time, half of it, in an entangled space. And when you then take a piece of paper with a magnet on top and on bottom, which is folded, and you pull the top magnet to the right, the bottom magnet on the bottom of the paper will just follow the top magnet. Why not? Yeah, because the paper is thin enough that the magnetic field will go through the paper, and it will not fall off. And every movement you make on the top of the paper, the bottom particle, which is seemingly completely independent from the top particle, is entangled and not independent, because the magnetic field keeps magnets together. I'm not saying that entanglement is magnetism. What I'm saying is this is a model where you can understand how it might happen.
Sure.
And when you then pull the upper magnet from the sheet, the lower will fall down. And there is no way when the upper is destroyed that the lower will not fall down. And that is exactly what is in EPR experiments shown. But that is a geometric explanation and not a superluminal one. When you want a superluminal one, you need a communication entity between these two in a non-folded space. And that might very well be a completely valid explanation. So what Emmanuel, when I had private conversation with him, was telling me is about that there could exist surface waves in the medium, ether, whatever. And these surface waves would be superluminal because they have no rotational amount. So they have nothing of charge which would make them curl or rotate, and hence they are not bound to the speed of light. Why would they? Yeah. They ride on the medium like a surface wave. And that can be very, very fast. And I think one of Emmanuel's core ideas is that gravity is such a surface wave on or in the medium. But then the medium needs more than 3 dimensions, because that you cannot by no means explain physically in the 3 or 4 dimensional world.
Don't they talk about the speed of light being a kind of fixed limit of causality as well? So even if the particle wasn't in, even if it wasn't connected to electric charge or something, it would still need to obey the rules of causality. It's just one.
Absolutely. So this is also my opinion. Causality is the primary reason. And when you think of it binary, if you digitize the universe in a holodeck and everything is virtual, literally it exists only in your brain or in the quantum computer to be called our universe, if there is one, then distance is a non-physical entity. It is a bit and a byte in an arrangement of avatars in this quantum computer. You want to move the X position of one of the players, change it. So what actually is moving? All the players get the information that that object has moved, and the quantum computer plays by the rules. So as long as you cannot bypass the programming of the quantum computer, or it's in the gear mechanic, everything has to follow by physical rules, because that is how things are moved. But would you have access to the code of the quantum computer by whatever way? Or change the X coordinate and the amount moves? There is no mass involved. Just change the X coordinate. It's rendered a different position instantly. And as weird as it sounds, you have to take into consideration such models, because more and more papers, especially those from Ed Berg, which are very, very interesting, show that you can replace all of current continuum mathematics. Sorry, Gerd, I wouldn't like to hear that, but has nothing to do with your ideas as such, because your equations are right with whatever mathematics you calculate them. you just don't like to see, from a psychological point of view, continuum go away, because it's this where we have been raised, or where we think our models fit best into. But if you digitize these models, they would do exactly the same, just with pixels and not with oscilloscope lines with an XY writer with an analog level of X voltage and Y voltage, which we perceive as a scope beam. It makes no difference if you have a digital scope or another scope. It shows you a picture. The TVs are exactly the proof of that, because the TVs had very, very complex beam generation mechanisms and tubes, and today they are pixels on a phone in high resolution. But when we look very, very detailed with a microscope, we see the pixels, and that's it. The interesting question from what Rajan said before is made me think a little bit. Is there really a difference between image, video, audio, and information and such in the colored level diagram which he has given? Because a video is a sequence of multiple photos. Is audio a different thing than a video? This is a question. When you can read lips and see a video, you can read the audio of the lips. So in a sense, experimentally can prove that video is containing the elements of the audio and the reverse. So everything is a matter of compression, when you put it mildly. When you have a film and you zip it with the zip tool, it compresses. But it cannot compress below a certain level. When it has the maximum compression ratio, the entropy is minimal. And that means you cannot compress it anymore. When you encrypt it, it gets bigger and not smaller. When you encrypt something which has a lot of zeros, you can get it smaller by encryption, but not when it's already NP complete random in the sense. When there's absolute randomness in it, you cannot compress it.
Wait a second though, can't you use, is it RSA encryption? Am I saying that right? With the where you can encrypt something, I might have this wrong, but let's say it's a certain number of bytes, and then every message you encrypt is always the same number of bytes, no matter the length.
No, it had nothing to do with the algorithm we use. It's a principal physical mechanism. We're talking about Shannon theorem. So the Shannon theorem says that you, by principle, cannot encrypt something. Also, encode is a better word. Yeah? Rewrite the bits in a way which makes a shorter amount of information for the same amount of info before. When I say this is a tree, you know a lot about a tree. I said, what tree? Is it green? Has it leaves? Not that detailed. I just told you a tree. And I tell you a tree in the summer in Munich, you might think of a beer garden, and you know already how the leaves looks because you have been there. Yeah. And it's shadowy under the tree, and maybe you can even paint the tree without me telling any more than this sentence. So I gave you 16 bytes in a sentence, and you can create a megapixel array or tell that sentence to an AI, and the AI will paint you the complete perfect tree. So what the AI is doing is decrypting the sentence and generates a tree out of 16 bytes. And it looks perfectly like a tree if you zoom in, because the AI knows exactly how the leaves of the tree look, how the growth of a tree needs to look, and the structure, the proportion, everything. So the digital theory of a tree is a fun thing, because how do you know the tree is real when you haven't cut it off? You see the outside of the tree as a texture, like in a 3D game. And when a 3D game renders things fast, and I have played a little bit with Unity and all these game engines, but they're not gaming, but for the sake of understanding of 3D voxel graphics. And they see rendering artifacts because they work with edge geometry. So they have edges and points and vertices, which means they have infinitely thin lines describing the geometry. And that is already the problem. You cannot do a perfect geometry with infinitely thin lines, except you have a very, very clever algorithm. I have written such an algorithm when I was age 16, so I really know it's a plotter algorithm, where you would draw on a plotter, and a plotter is slow. So imagine you have a pixel graphics, and you start with a white sheet, and you paint the house and the roof, and then on front you paint the door and the windows, and then you assume you want to paint the curtains. But how do you paint the curtains when the window is already there? The window in a children's image is easy to paint that way with a couple of colors. But when you want the full reflection, quantum mechanical of glass, then you need to understand what the light is doing when it goes through glass atoms, and you need to do a different way of rendering than games do. You have then ray tracing, and if you do ray tracing, your amount of pixels resides the amount of computing power you need to do. Modern graphic cards can, by the fun, do the same both, with both algorithms, even in real time. What I'm trying to express is all that rendering something on a screen which looks real is a way of compressing things. And the algorithm doing the compression of the universe, which makes us believe we see what we see and feel what we feel, can also be just data. And if it is just data, all our arguments of physical rules and physical, even the I-space logic of quantum constants of nature is somehow a little bit moot, because the bits and bytes of the artificial rules of the code of the universe, which we don't know who wrote it, would be the relevant ones and not physical rules. Physical rules would be emergent from that code. And when you try to talk to ChatGPT, and I did that the last couple of weeks in the background, and the Wolfram people are running at the moment a ChatGPT Wolfram plugin. This is extremely, this is one of the most powerful things in IT I've ever seen. It blows your mind. I can give you the links if you want. I'm not sure if I'm allowed to give them away. It was a free registration webinar running the last week, half an hour every week. And Christopher Wolfram programmed a webinar where you see what you can do with simple code from Wolfram Alpha combined with ChatGPT, and it frightens you, because your thoughts become real in computing code. You tell what you want, and the thing programs that for you in front of your eyes.
Right.
Out of nowhere. This is frightening. And that means that we're not as clever as we think we are, and we're not, the intelligence of us is something which we cannot be so sure of.
Okay. Interesting. Yeah, when you were talking about entanglement earlier, it reminded me, I made this little animation, kind of computer mathematical animation. So the blue particle going to the right is the particle, obviously. The red one is the antiparticle. And they look like they're both going in their separate directions, obviously. And they look like two separate particles. But in fact, if I was, like, I wrote this 2 years ago, so the details are a bit fuzzy in my mind. But basically, these two particles are not actually two particles. It's one line growing. But the extent of the particle deletes everything in between it. So it looks like there's two separate particles, but there's actually just one line. So anything that happens to this side of the line would happen equally to the other. Okay. It was based on like concepts within complex numbers, imaginary numbers. Like if you multiply, you know, 1 by 1, that's 1, but minus 1 by minus 1 is also 1. But then in complex numbers, it's a little bit different. Like the square root of minus I is, well, that is the thing for complex numbers. But it was, so the idea was that it's inverted for complex numbers. So
see, if you allow me to interrupt quickly, have you had a time to look at that papers, at least some of them, of Edgar? Because
I actually haven't. No, yeah, that's a good point.
You should do probably until the next meeting, because I have read most of his stuff so far, and what he's essentially saying is deeply in my heart. I really completely agree with him. Complex numbers are for mathematicians. They should nothing to do with physics. Unfortunately, unfortunately, most of quantum mechanics and a lot of Riemann calculations needed complex numbers for purely mathematical reasons, for differential equation solving, exponential function, and these things. And one of the most prominent functions, the function of e to the power of I phi is sine phi plus I cosinus phi, or cosinus phi plus I sin phi. You know what I mean? The prominent equation,
I know what you mean,
which is lauded for hundreds of years, and I think it's just while of course mathematically correct, it can only work in a continuum. Outside of a continuum, it cannot work. So when you have a discretized, or if you have a single thing quantized, be it Planck, be it time, be it whatever, you have to carefully question if this is still allowed, what you are doing. There are papers about that to show why that is.
Well, yeah.
You're not just allowed to apply mathematical things of geometry with exactness, razor sharp exactness to discrete systems. This is just wrong if you do.
You know, what about the Pauli matrices, that, you know, that kind of idea, and a lot of
I'm not saying to replace practical equations. So when it helps you to solve an equation, it's a fine thing to do because it helps you understand something. So I'm not saying that mathematics is wrong or anything like that. Don't get me wrong, please. What I'm saying is, I try to do that in my bad English as precise as I can do. What I'm saying is these are not real. In quantum mechanics, the phase angle is everything. There's an equation which shows that with pluses, a psi, so a quantum mechanical entity with a phase plus another quantum mechanical entity plus another quantum mechanical, and each of that has a phase angle. And I was thinking they add powers or energies or whatever. No, they add phase angles. So they add a circle 30 degrees to the right, and it's minus 15 degrees to the left, and it's 70 degrees to the right, because everything has a phase in quantum mechanics. And in the end, when you know the game, you get the right phase angle, and then it correlates with your experiment. Because when you read the simple Feynman books, and I hope you did, and even the non-trivial ones for the ordinary people, like Sie belieben wohl zu scherzen, Mr. Feynman, or surely you're joking, Mr. Feynman, and the small book about quantum mechanics, where he says the QED, the strange matter of light, I think it's called. You can easily buy, it's 100 pages. Feynman itself shows didactically brilliant what happens when light goes through a glass window.
Yeah.
And it's all about reflecting at the glass edge input and turning a different angle. And why? Because a mirror is not what you think. When you carve out half of the mirror, it still reflects. So when you know what phase angle you need, you can carve out 90% of the mirror and only keep that part of the mirror which does the actual reflection. This is completely counterintuitive, but physically completely correct. It does do it because the rays go nowhere else than the quantum mechanically says where they need to by phase angle. Now, when the phase angle, I have to quit. Sorry, guys.
No problem, Christian. Thanks.
Stop. Bye.
Bye-bye. So,
yeah,
that was interesting. I don't know if do you guys want to continue on then, or do you have stuff to do?
Yeah. Maybe another 5 minutes. You want to wrap up something? Yeah. So
okay, yeah. Because you said you'd have to go, or all right, Rajan. So I was just checking. So
yeah.
I want to stop now and say goodbye.
Yeah. Good thinking. I think we might as well go, and I might see you
continue next week.
Great.
Until next week. Okay.
Great. See you later, Greg.
Thank you.
I'll end the broadcast.